So thank you for the introduction, and thank you all for coming here today. Today I would like to talk about sail drones and the acoustic data that we've been looking at. Just get set up here real quick. Oh, cool. So over the past month, I have been a part of a collaborative mission between two NOAA line offices. The Pacific Marine Environmental Laboratory, located at the Western Regional Center in Seattle, Washington, and the Pacific Island Fisheries Science Center, located here at the Inouye Regional Center in Honolulu. And the overall objectives of this mission is to study ocean atmospheric interactions and environmental effects on pelagic organisms in the central equatorial Pacific Ocean. So this is a very vast and remote region. So it's very hard to collect surface data in these regions because they're so remote. And especially for like research cruises, voyages can be very lengthy and super expensive, like $35,000 per day operating costs, as an example. So one approach that we could take to reduce this cost would be to use uncrewed surface vehicles, such as a sail drone, as you see here. So the primary objective of my internship and my role in this mission is to evaluate the use of sail drones to collect backscatter data on pelagic organisms for ecosystem-based fisheries management. So with that, we can improve models in these data-poor regions. So some of you might not be familiar with sail drones, so I would like to quickly talk about them. Sail drones are one type of uncrewed surface vehicle that are manufactured and deployed by Saildrone, which is a private company based in California. They run on a business model where they sell the data to customers such as NOAA rather than selling the individual vehicles. And I think that goes for a rate of like $2,500 per day, if anyone's interested. For this mission, we are using the smallest sail drone model that they have, which is the Explorer. For reference, there's a person there. These things are about 23 feet long or 7 meters. They run on wind-powered propulsion and have solar-powered sensors. So it's 100% renewable energy. Each sail drone is equipped with an array of sensors. For the Saildrone Explorer, it's equipped with 3 acoustic sensors, 4 atmospheric sensors, and 5 oceanic sensors. These are the methods of our mission. On June 22nd, 2023, this year, we deployed 3 Saildrone uncrewed surface vehicles from Oahu. As you can see there, this is before the deployment. They're in port right there, or it's got shipped over. We deployed Saildrone 33, 79, and 30. Each sail drone is equipped with a standard suite of oceanic and atmospheric sensors, but only one of them has the acoustic payload. The sail drones have sailed to the remote central equatorial Pacific since the 22nd of June. And I guess right now they're near the Kiribati exclusive economic zone, highlighted in red there. And this is a 120-day mission, so it should be done in October, I believe. We are utilizing an adaptive sampling approach to study air-sea interactions, surface CO2 fluxes, ocean currents, and backscatter data, which is what I would like to talk about next. If you're not familiar with backscatter data, backscatter is essentially the reflection of sound waves off surfaces within the water column. So this could be fish, crustaceans, whales if there are any, submarines, whatever. And we measure this in kilohertz. We typically use frequencies of 18 to 200 kilohertz frequencies. And essentially, the lower the frequency we use, the deeper in the water column the sound waves can penetrate. So if this podium was the water column, 200 frequencies would only go like to this depth, but like 38, for example, would go all the way down there. So each organism has a frequency specific backscatter. For example, if we're looking at micronecton fish, which I'll explain later, they dominate the 38 kilohertz frequency. And this can be influenced by their body shape, size, orientation in the water column, and whether they have a gas bladder or not. For this mission, we are looking at 38 and 200 kilohertz frequencies down to 1,000 meters in depth. To measure backscatter, we use a device called an echo sounder. It's composed of two main components, the transceiver and the transducer. Then the transducer sends acoustic frequencies down into the water column, as you can see here with this graphic, and it also picks up the acoustic frequencies that are scattered back to it. And what this gives us is an echogram that looks like this. And this is actually a screenshot from the Saildrone mission portal that we use to view live data and updates from our deployed Saildrones. The x-axis represents time. This specific example is from July 3rd to July 8th at 5-minute intervals. This echogram also shows day and night intervals, which will be important here in just a second. The y-axis represents depth. We're looking at a depth between 5 and 1,005 meters. The pixels on this echogram represent the density of organisms, and how we view that is by measuring it in decibels, which is essentially proportional to density. The red, orange, and yellow pixels that you see on the echogram correlate or correspond to a high density of organisms. The green can be interpreted as like a moderate density, and the blue and gray can be interpreted as background noise or a very low density of organisms. What we could actually see from this echogram are the daily vertical migrations of micronectonic organisms. For example, near the surface or the epipelagic zone, we could see these clusters of green, yellow, red, orange pixels right there. And that is part of their daily vertical migration at night, where they feed near the surface. And during the day, we could see that they've migrated back down to about like, I'd say like 300 to 400 meters down. And we could see those clusters there in the mesopelagic zone. So micronecton are essentially organisms between 2 and 20 centimeters in length. They account for a substantial amount of biomass in the pelagic regions, and their daily vertical migrations are important for nutrient cycling and carbon transport between the mesopelagic depths, between 1,000 and 200 meters, and the epipelagic depths, the upper 200 meters. So the next steps in my project, I've only been working on this for like a month, but once we get the data back in October after the mission is over, we plan to process acoustic data to assess relative biomass and to assess how environmental variables may influence micronecton distribution, biomass, and composition. And with that, I'd like to acknowledge my mentors and everyone else who has helped me through the project. And does anyone have any questions?